So the last little section that we're going to do for this particular unit is looking at substitution elimination, particularly centered around oxygen, and if we're going to get more specific, around the alcohol functional group. So our alcohol functional group is shown here. We would really need to specify all of those atoms to identify it as an alcohol, because if we made that atom an oxygen and a double bond, we now have a carboxylic acid. So we really need a sizable amount of detail there to be able to label it out as an alcohol. So let's push to its reactivity. So if we go through and look at oxygen, it becomes really synthetically useful due to, number one, the lone pairs. Okay, why does that make it useful? Well, those lone pairs now mean it is a source of electrons. So it could become an electron donor. And since it's an electron donor, that means we're looking at it acting as a nucleophile and or base. Okay, well, the other reason why our oxygen is special is that oxygen is the second most electronegative element. So it's got a very high electronegativity. So with that high electronegativity, what is it doing to the atoms nearby? Well, it starts to withdraw electrons from those atoms. So those atoms become electron poor. So neighbors become electron poor, which then means they could accept electrons from somewhere else. And we now have the potential for electrophiles and for acids. Okay, so synthetically that's cool because we now have access to all of our potential reactivities. But if I run a reaction, who's to say in that reaction the oxygen is going to act specifically like a nucleophile and not as a base? So we have to be a little bit careful with that. The nucleophile base one becomes a little bit, I don't want to say obvious, but easier to go through and see because it's just those electrons. The electrophile and acid definition can become trickier. So let's go through and label those. The carbon, where the oxygen is connected, is going to be partially positive because the oxygen is withdrawing electrons. That makes that carbon potentially electrophilic. Okay. The hydrogen, where the oxygen is connected, is also partially positive, and that's going to make that hydrogen potentially acidic. Note, it's not going to be electrophilic because it's a hydrogen. And so if it accepted electrons from something else, we were talking about the transfer of a hydrogen ion, which makes it an acid, not an electrophile. So we've got lots of chemistries available to our alcohol functional group. And so for that reason, it can be a very bad functional group. So that means when we're looking at our reactions for our alcohols, a lot of what we're trying to do is to force certain chemistries to dominate over others to limit some of those side reactions. So one of the big first steps we could do would be like, well, damn, the alcohol sucks. Let's get rid of it. Let's replace that alcohol, say, with a halogen. Because if we had a halogen, the chemistry is now drastically reduced as far as the amount of chemistry available to it if I could put, say, like a bromine on there. So the question becomes is how can I do that conversion? What tools do I have in my arsenal to be able to pull that off? Well, if that chemistry is supposed to happen, what needs to occur? Well, I would need to break the bond between the carbon and the oxygen, and I would need to make a bond between the carbon and the bromine. So I would need to supply, say, bromide as a nucleophile so that it can potentially share with our positive, but at the same time get the hydroxide to leave. Therein creates one of our problems. Hydroxide is a horrible leaving group. So to get this reaction to occur, I have to make that leaving group significantly better. How do I make it better? Well, what would stabilize that negative charge? How about if we had another hydrogen? Then it would be water. So if I could change this structure so that it had another hydrogen on it, then the oxygen would be positively charged. That's now going to allow the reaction to occur. So if we can think about what chemistry we want to happen, we can then say, well, what do we need to change about this to force that chemistry to occur? Okay, so if we walk back through this, what did we say we needed? Well, we needed bromide, so we can erase that from our system now. We also needed that hydrogen, so that we could make that a good leaving group. And so what do we need to cause this reaction to happen? I could add HBr. The hydrogen, as a strong acid, will react with the oxygen, forcing it to act as a base, form a great leaving group. The bromide can now come in, force the water off as a leaving group, and I now have my alkyl bromide. The chemistry of the alkyl bromide is now solely left with that carbon being my potential electrophile, which is really neat. So that can help simplify some of the reactions that we could get out of these. And so behind this kind of argument or this presentation of how we're looking at this, what I'm trying to get you to think about is think of the reactions that are possible. Think of the mechanisms that we move through. Think of the reagent function or capabilities, okay, those reaction types that are listed. Okay, our electrophile base, nucleophile, base, electrophile, and acids. If we can think of our structures as those kind of reagents and think based off of atoms and their reactivities, we can start to predict things that would happen even if we've never seen that reaction before. And that becomes the power of this argument, and that's why I like Carty's organization behind organic chemistry. If you go through and use another textbook, what they're going to reference is instead functional group and say, well, alcohols react this way. Well, why are they reacting that way? Address the underlying chemistry, and now you don't have to memorize quite as much. Okay, so it can simplify it. Again, we're at the end of the semester. You may just decide that, hell with it, I just got to memorize some reactions. That's cool. Remember all the ones that we showed you? Here are a few more. So when we're looking at our alcohols, we can add strong acids. Those strong acids will go ahead and convert the OH into a good leaving group, which now gives us access to all of these potential other chemistries. Okay, and that becomes kind of neat and fancy. You'll notice that some of them come in with extra pieces, like for HCl, we need zinc chloride. Why do we need zinc chloride? Well, we need a catalyst because even the the chloride isn't a strong enough nucleophile to eject the water easily. The zinc chloride comes in and makes that oxygen an even better leaving group. So some of these cases make sense, some of them don't, and that's where if you have the chemistry background behind it, you can apply and try and predict what's happening without having to drill into some of the nuances behind them. Officially, you are responsible for reagents. Okay, that's part of this. So you could have to go through and memorize a lot of that. Remember, it's a multiple choice test for the most part, which means use your multiple choice answers to help you kind of reason through some of those choices. Okay? As we continue for alternate activations, there are other ways you can make that alcohol into a good leaving group so that you can force these other reactions. Most of these reagents, in my opinion, are second semester reagents, so we're not going to talk about these ones. Okay? The past ones over here were all following basic mechanistic patterns that you already knew, and you may just not have acknowledged that application process. Okay, so with these ones, if you want help, I have no problems drawing these ones out, but for simplicity and time's sake, I'm not going to draw them out right now. I'm going to leave that to you to try and play around with and see what you can come up with. For these ones, you might look at it, see that they're there, and just kind of accept it. Okay, if you got them, great. If you don't worry about them. These ones become trickier because notice we get stereochemistry coming into this. We're getting weird symbols like what element is TS? It's not an element. It's a functional group abbreviation. TS is tosyl. Okay. This would be a tosyl group. This whole thing is TS. See why we write it as TS now? We'll talk about that in second semester if you're going to stick around and deal with second semester. or enjoy second semester. If you're not, then don't stress about these. These aren't going to be your big kind of breakers for your overall reactions. Ether synthesis. So when we go through and look at alcohols, you will notice that if we went back a few slides that we did see that. If we had H2SO4 dilute, we could end in an ether. Well, what's happening with that? So first off, let's simplify this structure and let's make this ethanol. If I add a dilute acid, okay, it's going to supply H+. H+ is the most reactive thing. I'm going to react that alcohol, and I'm going to end up with now this great leaving group with that positive oxygen. Okay, and herein lies a problem. How do I permanently stabilize that positive oxygen? Okay, well, the statement of dilute means we don't have a lot. Okay, why is that important? Well, while I have a good leaving group, what do I have to potentially replace that leaving group? What I would need would be a source of electrons to be able to come in to share to make that. Well, is there a source of electrons, say, on my alcohol? Yeah, there is. I could have a second equivalent of the alcohol come in and attack. What's the result? I would form a new bond. I would have yet again another positive oxygen, which would be potentially unstable, and this is where another equivalent of my ethanol can come in with electrons, remove that, and I could end at my final ether, in this case, diethyl ether. And I've now done a full synthesis. Okay, and what we're trying to do is address the reagents or the chemistry of those individual atoms as we move through. One of the big things that students seem to miss is this kind of clutch step in the middle. Okay, where did that second molecule come from? Okay, where it just kind of appeared. Okay, how did I know it was there? Well, when you run a chemical reaction, are you reacting single molecules? Does a chemical reaction ever represent a single molecule reacting with other single molecules? No. Okay. Most chemists don't have the ability to control things at a single molecule level, which means we are looking at vast mixtures of these things. So we're looking at billions upon billions of molecules, which means that second molecule was already there. Okay, there's an artifact, and I would call it actually, an artifact from Gen Chem where we assume that the amounts of things are specified always in our chemical equation, and the amount is sometimes specified and it is sometimes not. Typically for organic chemistry, it is not specified. The few cases where it is specified is where we're trying to provide that extra clarity to help ensure that people follow the path we want them to follow. For whatever reason, we have decided as a field that we don't want to make that path as humanly obvious as possible by saying, adding a 2 times in front, or even for the sake of this one, doing 3 times because we had another one come in to deprotonate. Okay, so why do we not do that? I don't know, but that's not an argument for right now. The argument we've got is that second molecule is there. You're responsible for knowing it's there. You're responsible for acknowledging how that piece comes together. Okay, so ether synthesis, we can make a good leaving group, okay, which is what we went through and did here. We activated our leaving group. So we could look at this as an activation of the leaving group through acid-base chemistry. The other option is if we go through and we look at the nucleophile. You'll notice that the nucleophile here was our starting material, but it's a weak nucleophile. For it to actually work, we needed a really good leaving group. Okay, so the other alternative to going through and making a better leaving group is to force the leaving group off hydroxide, make hydroxide leave the structure, by having a better nucleophile come in and chase it. This is known as the Williamson ether synthesis. And this becomes a better synthesis overall, or not necessarily better, but a more versatile synthesis, because when we're looking at our make a good leaving group mechanism, the end result is always going to be a symmetric ether. Okay? Because the weak nucleophile that we're adding is the same as the source substrate. Okay, so we're going to end up with a symmetric ether. If we follow the Williamson synthesis, we can throw in a starting substrate, and we can now throw at it a really strong nucleophile that has any variety of different pieces coming off, which means I can make an asymmetric ether. And so that becomes kind of the advantage of the Williamson synthesis, and that's why it is typically named, is because it gets a little bit more versatility in that the amount of ethers that can come out of it. Okay. The problem with that is that we have to make that strong nucleophile, which means we have to run a pre-reaction. That pre-reaction, instead of going through to make the nucleophile or the leaving group better, my pre-reaction is that my strong base is going to come in, and it's going to make that, instead of being a leaving group, it's going to do the opposite, and it's going to make that a really good nucleophile. Now that I have this strong nucleophile, now I can run step 2, where I can add in any form of electrophilic carbon. Okay, and in particular, you'll notice that we'll probably use a halide, because I want to minimize the potential side reactions, and my strong nucleophile can now backside attack and eject the halide. Okay, so the Williamson ether gives me a slightly broader application to making asymmetric ethers. That's one of the big reasons we use it. Okay. The other big thing that comes with our Williamson ether synthesis is it's now actually a synthesis. We're using 2 steps to come through to make a product. We have to decide what reagents we want to use in those 2 steps to make that final product. Okay. And to that end, we've got 2 molecules shown below that are both ethers, and they have different pathways to go through and make it. If we look back at our ether synthesis, what we are attempting to make is one of the ether bonds, okay, red or blue. When we go through and take a look at the 2 materials shown down below, we're talking about how we make either of those bonds. Okay. Why is that important? Well, do they both have to work? No. Okay. And that becomes the importance behind synthesis. So it starts to address the concepts of how do we make these final materials. Okay. So take a guess at it. Okay. So actually, no, I'll walk through the MTBE for you, and then you can go through and do the anisole. So let's do the red synthesis. So what I'm going to do is I'm going to think about how I would split that in reverse. So where did that come from? Well, that probably came from the oxygen as a negative and the carbon as a positive. Okay, why would I think about it that way? Well, oxygen is more electronegative than the carbon. Okay, the problem with this material is that those are charged species, and those can't exist, okay, in a synthesis. So I need to think backwards still, where I'm looking at the oxygen in one way, and I'll look at the carbon structure in the other. The carbon structure, if I think backwards, I still want that to be partially positive, but I need something connected to it so that it's not formally positive. I'm going to go ahead and attach a good leaving group. The halide would be a great option because that minimizes the secondary reactivity. Now really the only reactivity I've got is that electrophilic carbon. As to the oxygen side of it, if I'm going to think backwards, I would need to put on a hydrogen. And now how would I put this all together? So what we've done is done a synthesis using retrosynthesis arrows to work backwards. So if we walk through this, what we would start with is our alcohol. I would react it with a strong base. I know it's strong because it's negative. The base would go through, remove the electrons. I would now have my negatively charged nucleophile. I could then react that in a step 2. And in that step 2, I would now have my bromide substrate. The oxygen could come in and attack, eject the leaving group, and I would now have, theoretically, my MTBE. Kind of makes sense? Okay, so what we've done in red was what is known as a retrosynthesis. We wrote out kind of all of the work of how we could have built that structure. And then in the purple and black that we've written underneath is our standard kind of mechanism. Okay, do I need to do both? Yes, and here's why we need to do both. Once you've built out the retrosynthesis, you need to verify that your reaction actually makes sense. So by writing out the mechanism, you can now ask yourself at each stage of the game, that works. What do I mean by each stage? Well, we had step 1. The base comes in, removes a hydrogen. Yeah, that's a standard acid-base step. That makes sense. Okay, and the next one, I'm having the nucleophile come in and attack. That's happening as an SN2. There are conditions of the SN2 that are important. For instance, we need a strong base. Yep, I've got the strong base in the negative oxygen. So what's the big deal? I also need a substrate that is not sterically hindered. This is a tertiary substrate, okay? Which means I'm not going to get the SN2. Okay, that tertiary substrate hinders this reaction, and instead of getting the SN2, that negatively charged species is not going to act as a nucleophile, it's going to act as a base, and instead of getting my MTBE, I'm going to get the elimination product. Well, damn, that means my synthesis was wrong. Okay, so that red path was a bad idea. Okay, you run into dead ends in synthesis. So what we would hope to do is to go through and look at the blue path and hope it worked out better. So if we go through and split out the blue path, what do we end up with? Similarly, negative oxygen, and we might go through and say, well, CH3 positive. Hell no, there's no way we can have a primary carbocation. But we aren't saying that that necessarily has to form. We're just saying that that is our work process behind it. How would I get that? Well, I could get that if I had a CH3 with that Br leaving group. There's my bromine leaving group. Nice, sterically unhindered. That could work out great. How do I get my retrosynthesis of the T-butyl? Well, we could go through and put on the hydrogen. So I need to now think through how I would do this as a synthesis. Okay, so how are we going to start this off as a synthesis now? Well, we'd start with the T-butyl. We'd add our strong base, standard SN2, acid-base reaction. We go through, we form the strong nucleophile, and we now react it with that CH3 with the bromine leaving group. Comes in, attacks, ejects, and we now have our MTBE product. Go through and evaluate. We still have an acid base. This is an SN2. That SN2 wants a strong. Yep, this is strong. Okay. We also have a zeroary substrate, which also suggests SN2. For those of you saying, but, you're probably referencing that this is a bulky nucleophile. And wouldn't it therefore act as a base? Okay. It could, if our substrate had any aspect to it that would allow it to act as a base. Okay, that substrate is now so sterically unhindered that it's actually going to allow for the SN2 reaction to happen, and the blue pathway ends up being our better path. Okay, so what we do is think about how we would backtrack away from this, split those bonds, look where the charges fall, decide how we could make the species that has that kind of characteristic, okay, and then put it all back together as a synthesis and check and verify that each of those steps actually make sense. Okay, to that end, what I'm going to go ahead and do is clear everything away. If you didn't want that, then go ahead and undo it. We have the same process that you could initiate on the other side. We have the red bond and we have the blue bond. So go ahead and pause, come up with a retrosynthesis that you think is going to work, and then we'll just have it appear here in just a second. So remember, pause, space, click the screen, any one of the above. And ta-da, we get our answers. The red bond has that backside attack on our leaving group, which is just not going to fly in either an SN2 or if you wanted to try an SN1, also not going to work. So the red bond is not the bond that's made in this synthesis, and we'd have to go through and show the blue. Just to give you an idea on what could be shown in a multiple choice, we could say which of the following syntheses would go through and work with this, and we could say we start with, now I got to remember all the reagents. We start with OH and Br, or we start with OH and CH3Br. Okay, so those both look like they could theoretically work because they're showing the same proper pieces, but that one reaction, which is the red answer in our synthesis, doesn't actually stack up and work, okay, because we get that bad sterically hindered attack. So we have to remember and apply those concepts that we had way back when in our substitution unit, which was theoretically like 2 weeks ago, maybe even just a week ago, depending on when you're watching this video. Okay, so that's our little primer into synthesis. Second semester does a hell of a lot more with synthesis, where you now have to apply all of the reactions. This is why exam scores tend to fall through the floor in second semester, because you're expected to know all of these reactions we've addressed and more, and now how to put them all together into one big happy puzzle. Okay, so I think the last big one of this slide sequence is looking at our epoxides. Remember the formation of our epoxides. We could get them when we used MCPBA. Okay, well, crap, since we've already started it, we're just going to go ahead and finish it. We can get our epoxide by reacting an alkene with MCPBA. MCPBA was that goofy three-membered transition. We're looking at the oxygen of our meta-peroxybenzoic acid. That oxygen is great to be attacked because it has this leaving group, which, because I really like showing this mechanism, and I don't think I've shown it recently, that leaving group is phenomenal because it does a couple things for us. And we can actually get this fantastic, awesome looking mechanism with arrows flying out the yin-yang, which is really cool and just kind of scary all at the same time. And the end result that we get would be our epoxide with the oxygen in the middle. Because it all happened in one step, these methyl groups are going to be stuck on the same side, either both wedged or both dashed. Because there's an internal line of symmetry, there's only one product in this case, regardless of which way it attacks. So, cool, we now have an epoxide. What becomes special with the epoxides? Well, the epoxide, as you might guess, becomes a stressed structure. It's stressed because we have a three-membered ring, okay, that are all those carbons sp3 hybridized, meaning they want to be 109.5 degrees. So that three-membered ring being stuck at 60 degrees is trying to break open. For it to break open, that oxygen would need to take electrons from one of those bonds. Okay, so either red or blue. Depending on the conditions, red or blue is favored. Okay, so let's walk through our conditions for our basic or neutral system. If we're running under basic or neutral conditions, we're going to have a strong nucleophile. Okay, the neutral is a bit of a misleader, but the basic can help us out. Basic conditions means we'd be adding things like, I don't know, hydroxide with what charge? A negative charge. So if you see basic, strong negatives are a good thing. Okay, that makes a lot of sense. Because it is a strong nucleophile, it's now going to attack one of those carbons, be it the red carbon or the blue carbon. So now the question becomes is which one? Okay? It will matter because our nucleophile would now be connected either to the more substituted or the less substituted position, and the oxygen would be connected to the other. So how should we make this decision? Okay? Well, since it's a strong nucleophile and we're looking at kind of a bad leaving group, okay, this reaction is going to happen as a direct backside attack, and the nucleophile must force the leaving group off, okay, which means the nucleophile must get to that electrophilic site. Which site is the most accessible electrophilic site? Our red site or our blue site? The red site is less sterically hindered, which means the red site is more likely to happen, and our epoxide will open with the oxygen connected to the blue carbon and our nucleophile connected to the red carbon. What becomes particularly of interest here is a couple things. Number one, we've got a regiochemistry difference here. That regiochemistry, note the nucleophile is connected to the least substituted position, and that oxygen of our epoxide is connected to the most substituted position. Okay, so there's a big regiochemical effect here. We also have a stereochemical effect. That oxygen is aimed up, the nucleophile is aimed down. They were added on opposite sides of the ring, okay, or they end up on opposite sides of the former ring, which means we have an anti-addition. This becomes a little bit weird to call an anti-addition because we don't have a pi bond that we're adding to, but we are adding across the ring and realize that our rings and pi bonds have similar nomenclatures. Okay. At this stage, we don't have a final product because we have that negative oxygen. To stabilize that, we can follow this up with a step 2, H+. Why does it have to be a step 2? Well, if we added H+ with the strong nucleophile, the H+ would have canceled the nucleophile. Okay? So we have to do this as 2 steps. There's our nucleophile. Our stereochemistry is maintained. There's our OH, and we've got our final product. Okay? One of the things that might stamp or jump out at you here is that we did say that this was basic and or neutral conditions when we ran through this reaction, and that those conditions drove the chemistry of the reaction on where these groups were, which should be suspicious because the opposite of a base is an acid, and we could run this under acid conditions. And that is indeed what we'll see as we advance the slides. If you wanted to look at pretty drawings as opposed to my hand-drawn colored ones, there are pretty drawings underneath kind of showing those steps. If we run under acidic conditions, well, now the system changes. Why does it change? Well, first and foremost, we have an acid. So the very first thing we need to do is not worry about the ring, but worry about the acid. The acid is now our priority. How do we stabilize an acid? Well, we would need electrons. Where do we have electrons? The oxygen in our epoxide. The result, that was horribly drawn, the result is that we now have that oxygen with a hydrogen connected to it. Why does that matter? Okay, well, what charge would the oxygen now be? That oxygen is now positively charged. It does not want to be positively charged. So we've now added a greater incentive for that oxygen to break away from that structure. So that oxygen is now screaming at trying to jump off the structure. Okay, because that added incentive is there, red and blue start to break prematurely. The question becomes is which one is more likely to break? Okay, The blue one becomes more likely to break because if it breaks, what would it form? It would form the carbocation at the more substituted position. If we broke the red one, we would get the carbocation at the least substituted position. Okay, so the red one ends up being a bad option in this circumstance. The nucleophile that now has this opportunity to stabilize the structure permanently can come in and attack at the blue position. So now we can show a difference, which is causing the ring to break open. Note that the nucleophile is drawn slightly differently than it was in the past. In the previous slide, the nucleophile was negative. In this slide, the nucleophile is neutral. Why? What conditions were we under? Under acidic conditions, we see the presence of H+. The charge that we should be seeing is positive or neutral. We should not be seeing negatively charged species. What's the result of this reaction? We'd end up with the oxygen connected over there. The nucleophile is still going to come in from the backside. So we're still going to see that anti-addition. Okay? That is a requirement of this. However, the extra benefit here, or the extra difference, is now where that nucleophile is located. In this case, the nucleophile is located at the more substituted position, and the oxygen from our epoxide is now at the least substituted position, which is the opposite of how it happened under basic conditions. And so the way I see a lot of people talk about this on the internet is that these are opposites and there's different chemistries. There isn't a different reaction. We're just focusing on the conditions that we're looking at. So if you can focus on the chemistry of the atoms that are present, deal with the chemistry of those atoms, not the functional group. The chemistry of the atoms will dictate what happens with your functional group. Okay? That is a trickier thing to manipulate and understand and deal with, but it can get you to the answer with knowing less about what the specific reagents are. Okay? But you can now apply that content to better things or to more advanced things. You'll note also in this reaction, we don't need a second step or a second reagent to deal with our charges here because we protonated the oxygen right out of the gate. Okay, that was part of the reaction. I don't need to separate the acid from the nucleophile because the nucleophile is a weak nucleophile, so the acid isn't going to be a real issue with that nucleophile. Okay, and with that, I believe we're actually done. I am going to caution you because I'm going to hit pause here real quickly. So my computer freaked out. This is actually technically at the end of this section that I wanted to cover. If you're looking at the slides, there are some subtle drawings or skeleton drawings started to be drawn for you. Those are missing some key atoms. You might go through and note that we don't see the lone pair on this, and that's because what's supposed to be replacing that lone pair is the hydrogen from our acid and that formal positive charge. So those structures were not completed all the way. Okay. Oh, dang, it does look like there's another slide. Okay, so I do have a slide that summarizes our epoxides. Okay, so for our synthesis of epoxides, MCPBAs or other peroxy acids, how do you know it's a peroxy acid? You're looking for our O3H. It's that O3H that's a big tip-off that you're looking at a peroxy acid. So really any peroxy acid, peroxy acid will go through and make your epoxides. Once you have the epoxide, you have to evaluate, be it under basic or acidic conditions. And of course, since I just copied and pasted that across, I'm going to have to show that stupid hydrogen. If we run it under basic conditions, our big difference is that we need a second step to add the hydrogen onto our drawing. Okay, if we run it under acidic conditions, we don't need a second step, but we do have to, or we do notice that the nucleophile comes in and attacks at a different position. And with that, we're actually done with our substitution elimination reactions. The only thing we have left for this semester would be our radical reactions, which is probably going to get split across 2 lectures. The overview and then the nitty-gritty details behind it. With that, I should just shut up, so I'm going to stop.